Today, I want to cover chapter 11, focus on interstellar medium. There are three major topics I want to cover for this chapter. The first part is interstellar matter, focusing on star forming regions. The second topic I would like to cover talks about the formation of stars like the sun at different stages. And then lastly, I want to talk about different kinds of star clusters. So from the lesson plans I posted today, actually there are three groups of terms I wanted you guys to get familiar with for this chapter. The first group has three terms: emission nebula, dark nebula, reflection nebula. The second group has three terms as well. The first one is 21 centimeter radiation. The second one is zero-H main sequence. The third one is brown dwarfs. The last group of terms I would like to ask you to get familiar with for this chapter is star cluster, open cluster, and globular cluster. So while I'm going through the PowerPoint files and talking about chapter 11, I want you guys to keep those terms in your head and then try to understand those terms. So the first group of terms actually focus on the star forming regions. As we mentioned at the very beginning of the semester, we talk about, I think I remember the first term we defined in this course is called nebula. So the interstellar medium consisting gas and dust is called nebula. So gas actually are atoms and small molecules, mostly hydrogen and helium. And then dust refers to soot or smoke, which has larger clumps of particles. And there are three different types of nebula I would like to ask you guys to get familiar with. Again, nebula is a general term used for fuzzy objects in the sky. So there is dark nebula, which is consisting of dust cloud, as you can see from this picture here. The second type is called emission nebula. Emission nebula has hot stars inside. It's going to emit light. And then the third type of nebula is called reflection nebula. Reflection nebula is going to reflect the light from nearby stars. As you can see from this picture here, we have three types of nebula. One is dark nebula, the other one is emission nebula, and then we have reflection nebula as well. So the following few pictures actually shows you the fuzzy areas in the different regions of the universe. Okay, the second group of terms I ask you to get familiar with. The first term is called 21 centimeter radiation. This is the method we use to detect hydrogen atoms in the universe. And we know that, nebula has abundant hydrogen atoms. And if we are looking for star-forming regions in the universe, and if we can find out the hydrogen abundant regions in the sky, it's going to help us to find our star forming regions. So what is 21 centimeter radiation method? As you can see here, the hydrogen atom has one proton, one electron. So electron is orbiting around the proton. Okay, so the protons, both protons and electrons, they spin. So as you can see from this picture here, if protons and electrons actually they are spinning in the same direction, we call this parallel spin status. If the proton spins this direction, electron spins the opposite direction, we call this anti-parallel spin status. When hydrogen goes from parallel spin status to anti-parallel spin status, it's going to release energy. The emitted photon has wavelength of 21 centimeter. That's where the name comes from. So by detecting this emitted photon, we are able to find out, okay, indeed, this region has a lot of hydrogen atoms, which is going to help us to find out the star-forming regions. Okay. All right, so the next topic I'm going to talk about for this chapter is going to be the formation of stars like the sun. If you still remember when we talk about the solar system formation, okay, it all started from nebula, okay, and then because of the gravitational force, okay, it's trying to pull everything towards the center, and that's why the center of the nebula is going to become very hot and very hot and dense. Okay, once the center temperature and density reach critical levels, it's going to begin nuclear fusion reactions. During the fusion reaction, hydrogen atoms are combined together to form helium atoms. And then when this happens, photons of light are emitted. So we are going to see in more details, step by step. So at the very beginning, if you only have a few atoms, the gravitational force is not going to be strong enough to overcome the random thermal motion. And okay, so when the interstellar cloud starts to contract, okay, probably triggered by a disturbance such as a shock wave from a supernova, is going to trigger the cloud of gas and dust to spin and collapse inward. Okay, as it contracts, the cloud fragments into smaller pieces. The individual cloud fragments begin to collapse. Once the density is high enough, there's no further fragmentation. But in the meantime, again, remember, the inward collapse of materials causes the center of the protostar to become very hot and dense. Okay, once the central, and so then, you know, the temperature is going to increase. And this picture shows you the Orion Nebula region, which has some protostars forming here. Okay, and the core of the cloud is now called protostar. Okay, and makes its first appearance on the HR diagram. So that means there is luminosity, the temperature is high enough. And the last stages can be followed on the HR diagram as follows. So the protostar's luminosity decreases and temperature rises, okay, because it's becoming more compact. At stage 6, the core reaches 10 million Kelvin and nuclear fusion begins. The protostar has become a star. So at stage 6 here, okay, the core reaches 10 million Kelvin and nuclear fusion begins. The protostar has become a star. And the star continues to contract and increase in temperature until it is in equilibrium. What do we mean by that? Okay, remember, the inward collapse of material causes the center of the protostar to become very hot and dense. Once the central temperature and density reach critical levels, nuclear fusion reactions begin. During the fusion reaction, hydrogen atoms are combined together to form helium atoms. When this happens, photons of light are emitted. Once these reactions are sustained, the protostar becomes a main sequence star. So what do we mean by that? At this time, the star no longer collapses, and the state of hydrostatic equilibrium is reached between the inward gravitational collapse of material and outward pressure caused by the energy given off during nuclear fusion reactions. If those two are balanced out, so we call this hydrostatic equilibrium. When a star has a hydrostatic equilibrium, we call this star as a main sequence star. And when the star first appears as a main sequence, we call this 0H main sequence star. If the mass of the original nebular fragment is too small, nuclear fusion will never begin. These failed stars are called dwarf stars, brown dwarfs. So that's the third term from the second group of terms actually I ask you guys to get familiar with. And if you can take a look at this diagrams, which has stars of some other masses. Okay, this one has 0.3 sun's mass, and this is like the sun star, and then this is 3 times of the sun's mass, and they all follow very similar shape. Okay, but they wind up in different places on the main sequence because they all have different surface temperature and they probably have different luminosity. The last topic for this chapter, we talk about star clusters. Okay, because a single interstellar cloud can produce many stars of the same age and composition. So star clusters, they are a very good way to study the effect of mass on stellar evolution. And we are going to compare 2 different kinds of clusters. One is called open cluster, and this one is a cluster called Pleiades. If you plot the stars on the HR diagram, you can see majority of the stars from this Pleiades actually are main sequence stars, and some of the stars actually they are blue giants. This is another cluster which is called the globular cluster. Okay, and if we plot this, the stars from the globular cluster on the HR diagram, you can see it's very different from the previous cluster HR diagram. Majority of the stars actually they are moving away from the main sequence, and they are becoming red giant stars. So by comparing the HR diagram of these 2 clusters, we can see open cluster Pleiades actually has a lot of young stars. Okay. On the other hand, the globular cluster, they are mainly populated by the red giant stars. So it is a much older cluster. And these images, they show star cluster formation within the Orion Nebula. Okay, so that's all the topics I want to mention for this chapter, and this PowerPoint file is available on the Blackboard, as well as the lesson plan I posted on the Blackboard. And the last thing I want you guys to do is I want you to work on the worksheet titled as Star Formation and Lifetimes, and which will give you more information about star formation and how mass of the star is going to decide the lifetime of the star as a main sequence. And later on, when we talk about how the stars are going to die eventually, how the stars are going to leave as a main sequence star, and you will find out that mass actually is a very important factor to decide which path the stars are going to go down the road. And next class, I'm going to come back to talk about the worksheet I asked you guys to do, as well as we are going to cover some new materials.